Hello everyone, in this tutorial we're going to work on star calculations, which is using FITS data. FITS stands for Flexible Image Transport System, to measure stars number, apparent luminosity, magnitude and temperature. So basically a FITS image is a Flexible Image Transport System file, which is a file type used for astronomy scientific data. FITS data is made of two main sections mainly. The header, which has the metadata for the image, such as information about the telescope, observation type, instrument used, data of observation, zooming rate, etc. And the core data, which is made of pixel data for an image that contain the brightness, the amplitude of the signal, the magnitude, so to speak, that is collected based on the image visualization, based on the captured image data itself. So FITS contains photometry data, astronomic measurements, spectrum and frequencies, analyzing the relative position of stars, temperature of stars and galaxies, atomic composition, stars movement. Actually, this is what we can collect from a FITS data. Okay, so we may not have necessarily the temperature, but we can measure the temperature by relying on the luminosity and other factors. You can also detect astronomic events such as a supernova and many other things related to astronomy. Okay, one of the things that we can also do is counting the number of the stars in a FITS file, which is done by tracking the number of light spikes, the peaks within the matrix when they cross a specific threshold, because you have noise within the picture, you have contaminants due to the lens of the telescope. However, you can make it in a way that when you cross a specific threshold, you can consider that this point of light is intense, like we see here in this image, background image. When this point of light is intense to a specific threshold, it has a specific magnitude, so to speak, you can count it as a star and you can add it up. So you can estimate the number of stars within an image, like the background image we see in this picture, like the background image within this presentation. We can measure also the brightness of a star. So let's say you have a star like this one. So you can measure the brightness of the star, which is actually the sum of brightness of all encapsulated pixels inside the range of the disk of the star, which is basically what the equation of the circle x minus x0 square plus y minus y0 square should be less than or equal to the radius, meaning all pixels that are located either on the circumference of the disk or within the disk. So you collect the amplitude signal of all these pixels and you add it up to get the brightness, the apparent total brightness of the star. Apparent magnitude, you can get it from the apparent brightness. You can get the apparent magnitude, which is m, from the apparent brightness, which is I in this equation. So m equal minus 2.5 log base 10 I plus c. Finally, we can calculate the star temperature by estimation, of course, using the formula luminosity equal 4 pi r square, r being the radius of the star disk, times sigma, which is, by the way, the Stefan Boltzmann constant, times T to power 4, T being the temperature of the surface of the star. So T K0, because the temperature is in Kelvin, is equal to square root at the fourth level L divided by 4 pi r square times sigma. So this is how you can get an estimated value for the temperature. Okay, so in order to work with FITS data, we needed to download a FITS file. I used this website that will be provided in the description, remoteastrophotography.com/sample downloads. And I'm using the Messier 51 FITS, which is a galaxy, by the way. And we will open it in Google Colab. Now you have multiple files belonging to this FITS data, but what I'm gonna use is the luminosity file. So let's drag and drop in the Google Colab files. Okay, and the file has been uploaded. At first we need to install two main libraries necessary for Astronomy Works. So pip install AstroPy, pip install SciPy. Let's import NumPy as well, NumPy as np to work with matrices, and import AstroPy from astropy.io, import FITS to be able to read a FITS file. File name equal M51 lum or luminosity.fit, which is this file we just uploaded. With fits.open, let's open the fits file. File name as hdul hdul.info. Let's get the info of the file. Primary hdu equal hdul0, the first dimension of hdul. hdu data equal primary hdu.data, because we have data and header. hdu header equal primary hdu.header. That's the hdul info. Let's print the header. Print hdu header. Okay, which contains again the metadata for this file. Now let's check the shape of this file. We know that it is a 2D array, but how many rows and columns does it have? hdu data dot shape, 874 rows, 973 columns. It's basically an image, a capture of the universe in that area of the galaxy. Let's plot the image to see what it looks like. So import matplotlib.pyplot as plt, plt.mshow hdu data, cmap gray, plot it in a gray mapping, plt.colorbar, and plt.show. If we look closely, we can see the galaxy almost in the middle. Actually, you have two galaxies close to each other, but they are not too visible right now. Let's try to smooth the image to remove the noise and to clarify the important info, like the entropic info for this image. From SciPy, import nd image data equal hdu underscore data, smooth data equal nd image dot Gaussian filter, which is a filter for noise in the image. Data, which we collected from hdu data. Sigma is the proportion of filtering or cleansing of noises. So sigma equal 2. That would be the filtering or smoothing ratio. Threshold equal mp.mean. Here we are getting the threshold, which is the threshold of smoothing. It is equal to the mean, which is the average of all pixel brightness, smooth data, plus 2 times np.standard variation for smoothed data. So the threshold is the value in the middle, the midpoint, if you will, of all brightness within the picture, plus 2 times the standard deviation, which would give you the average value of all brightness of the picture added to a standard deviation which will make the stars and other stellar objects stand out. Loco maxima, which is the maximum point of a certain locality, of a certain region, equal in the image dot maximum filter smooth data size equal 5 equals smoothed data, and smooth data greater than threshold. Okay, so the loco maxima represent the stars. This array will contain the number of stars basically. Why? Because it is detecting the loco maxima, or the maximum brightness point in all the areas of the image. It is detecting the regions where you have a maximum spike of brightness within the image, or namely stars. So the loco maxima will be an array that will carry all the points within the areas of the image where these points have the maximum brightness. This is what we mean by loco maxima. Namely, this will be an approximation or an approximated estimation of the number of stars within the image. So to get the number of the stars, labeled image num features, number of features, equal nd image dot label, and this is a tuple here at the beginning, dot label loco maxima. Next, we need to print the number of stars, which is the number of features. Print number of stars within the image is the num features. Let's run it, and you get approximately 90 stars. Now let's show also what this image would look like. Let's plot the smoothed data. plt.mshow smooth data cmap equal gray plt.color bar plt.show. And if you notice, we have a much better image than the one we've gotten originally. Why? Because we've smoothened the image, much of the noise has been cleared, and the vision of the stars and the galaxies has become more accentuated, meaning that they have become more clear and discernible within the image. There's another way to count the number of stars, and let's present it. So what I'm gonna do is flatten this matrix of image into a one-dimensional array to pick up individually different spikes within the image. And the spike would be the peaks of the image, the fluctuation of light. As for example, here in this dot, you would get something like this up and down visualization, a peak, okay? And we can approximate the number of stars by picking up the number of peaks, even without having to clear the image from noise. You can set the threshold as being 1 point something, like in our case 0.15, let's say. And anything that has a light intensity greater than 0.15, we can consider it as a star. We get all the peaks, all the fluctuations of light within the image, and any fluctuation greater than 0.15 or 0.10 would be analyzed or processed as a star and counted. You can almost get the same value we've gotten using the smoothing filter. So let's start with it. So data flat, we're gonna call it, equal HDU data flat equal data flat dot reshape -1. Reshape -1 would convert the 2D array into a one-dimensional sequential array. And let's plot the data flat Since it has become a 1D array, we can no longer use the mshow, we use the plot, since it has become a curve rather than an image. And you notice all of these high peaks can be considered as stars. Let's at first print the data flat. These are different values for the flattened array. Okay, let's get the peaks. So from scipy.signal import find peaks. Peaks equal find peaks, data flat, count equals 0, we'll start with 0. So for peak height in this array, which is storing all the peaks within the data flat. This is a function that finds all the peaks within a curve. So for peak height in data flat, and within data flat, I'm looking for peaks 0 for each row, meaning, okay, and column. If peak height is greater than 0.15, then we will consider this threshold as being a high intensity enough to be a star or a stellar object rather than an image noise. Count plus 1 added to the count of the number of stars. Finally, print count. Let's see what happens, and you have 97 stars. Around the same value we've gotten by smoothing the image. It's almost the same result. Alright, so basically the peaks are the different signal powers where you have a concentration of the light signal within the entire map that has been flattened and reshaped into a one-dimensional array. So when we print the peaks, you can see that it's a one-dimensional array with multiple values. If we type peaks, meaning give me the data type of peaks, it's a tuples, that's why you have 0 column, meaning give me all the values within peak 0, which is only one row. Within the first row indexed 0, give me all the values that are stored within that row. If the peak height is greater than 0.15, then count plus equal 1, meaning add up the count of the stars that have been discovered. Alright, so let's write a function to get the apparent brightness of the star. So def get star brightness. We need the data x, y, and the radius for that star. X, Y, of course, are the coordinates vis-a-vis the ND array. So let us at first get the indices or the coordinates for the data. So X indices, Y indices, which would be two matrices, by the way, equal mp.indices for data.shape. And as a reminder, data.shape would give you 874 rows by 973 columns. So I need X and Y coordinates for all these rows and columns intersections, or all these pixels, all these values. Star disk is equal, here we want to get all the pixels within the region of the star, which is composed of X and Y, of course, coordinates within the disk, having a radius r. Okay, that's why we needed radius. So star disk equal, and if you know already, the equation of the circle is x minus x0 square plus y minus y0 square equal r square, with x0 and y0 being the coordinates of the center of the circle. X indices minus x power 2 plus y indices minus y given within the function power 2 less than or equal to radius square, meaning they are within the disk. Give me all x and y coordinates within the area of the disk, not going beyond the radius of that disk. Star brightness would be the sum of all that data for all these coordinates, the xy coordinates gotten by this formula. Data star disk, return star brightness. Okay, another formula. Let us get the apparent magnitude for the star. So m equal minus 2.5 according to the formula times log 10, log base 10 of I, with I being the brightness, the value gotten from here, plus C or calibration factor. Okay. So def get apparent magnitude brightness calibration m equal minus 2.5 times np dot log 10 brightness plus calibration return m. Finally, let us get the temperature. So another formula for the temperature, the estimated temperature of the star. Here, note that for the temperature we need the luminosity, but here we have the apparent brightness. Okay, so we're gonna consider, although it's not accurate, we're gonna consider the apparent brightness as being the luminosity, although the luminosity should be computed using a different way. Luminosity relies on the apparent brightness, but it needs another factor which has to do with parallax. I won't get into that right now. Star temperature measurement sigma equal 5.67 times 10 to power minus 8 Wm watt meter minus 2 K minus 4 L equal luminosity equal 4 times radius square times sigma times temperature to the power of 4. So def get star temperature luminosity radius sigma equal 5.67 e to the power minus 8. So this is the same as 5.67 times 10 to the power minus 8. Temperature equal luminosity divided by 4 times np dot pi times radius square times sigma to the power of 1 by 4. Okay, so it is a square root, a quadruple root, not a square one. Okay, as if two square roots upon each other. Return temperature. So let us get a high value for MP. Okay, so let us get a high point, high power value within the matrix, a bright point, so to speak, and we will consider it as being a star. Actually, we will choose a value a little below it, and we will consider it as a star and work on it using these functions we've just created. So, max equal np.max smoothed data. Print max. We will pick 0.36 but we need to find where this 0.36 is located on the image vis-a-vis coordinates x and y. X, y equal np.where smooth data is equal to 0.36. Let us get the luminosity. So lum equal get star brightness. Actually, brightness is the more accurate word. X, y, and we will suppose that the radius is 5. So mag equal get apparent magnitude. We need the luminosity and the maximum value here. Finally, temperature equal get star temperature. Luminosity, which is apparent brightness, but we are considering it. If we get np.max, which is the max value, and consider it as a star, it will work out fine. You see, lum or luminosity equal get star brightness HDU data or smooth data. We can change it here. XY 5. Because xy is actually there. It exists where you have a value that is actually equal to the max. That's why. Okay, mag equal get apparent magnitude, luminosity 0.36674, etc. Temperature, and you've gotten the apparent brightness of the star, the magnitude, and the estimated temperature. Okay, thank you so much for watching, and we will see you next time.